Today, with this morning's symposium and the ceremonies this afternoon, we celebrate the life and honor the memory of Dr. Ronald E. McNair. Ron McNair earned his PhD in physics here, and we at MIT are very proud of him. Ron's life, which was tragically cut short, was marked by heroic accomplishment, courage, and dedicated service to his country. His record stands as a model for all young people to emulate and has brought great honor to his family, his friends, to this institution, and indeed to the whole country. As most of you know, at MIT we have a Center for Space Research, which shares a building with the Department of Aeronautics and Astronautics. And in the MIT tradition, this building has been known as Building 37 for the past several years. During the past year, there has been a groundswell of opinion that this building should be named for Ron McNair. Before this day is finished, Building 37 will officially become the Ronald E. McNair Building. I extend a warm welcome to all of you for this morning's symposium, and I'm especially pleased to welcome Ron's family and his many close friends who are here with us this morning. All of you, of course, are invited to attend the dedication ceremonies this afternoon and the reception which follows. And now it is my pleasure to introduce my colleague, Professor Gordon Pettingill, the Director of the Center for Space Research, who is the chairman of this morning's symposium. Gordon.
Thank you, Gene. This morning, in a program to commemorate Dr. Ronald McNair's interest in advancing science, as well as his deep interest in understanding how science affects man's outlook, we will hear from 4 speakers, all addressing a theme that was close to Ron's heart, the space frontier. Unfortunately, I was not able to know Ron directly, but from reading things that he has written, talking to people who knew him, his personal philosophy has come through very clearly indeed. This philosophy is, on the one hand, to think clearly, to exercise one's intellect, and to do careful planning, all of that's essential, but at the same time to push hard against the frontiers of knowledge, to take chances where they are necessary, and in fact to hang it over the edge. This last phrase, which is included in the symposium's title, was a favorite of Ron's. I gather that it originated in the surfing and mountaineering communities, perhaps otherwise as well, I don't know, where it epitomizes the daring that's necessary to make one's mark, even if it leads to danger. In Ron's case, it translates as a need never to let well enough alone, never to sit back fat and happy, as it were, and always to perceive and accept a new challenge. I'm sure that this theme, which is so characteristic of Ron, will surface again and again in the ceremonies today. As Dean Brown has just said, Ron had a very strong involvement with MIT, coming here first on an experimental program for talented undergraduates, and then later returning to earn a doctorate in physics based on research in the application of lasers to spectroscopy. His was an educational success story in every way. We'll hear more of Ron's personal life and recollections of people who knew him well in this afternoon's ceremonies. But in this morning, we're going to highlight those interests of Ron's which involve more the scientific and the involvement of man with science. We will hear a series of talks revealing how an inner drive, fed by the excitement of research at the frontier, has propelled scientists to reach out for an understanding of the heavens. We hope that some of this excitement and wonder will be felt by all of you. Our first speaker this morning is Institute Professor Philip Morrison, well known for his wide-ranging interests in all the works of man, including extraterrestrials too, if we can only find some. He suffuses the discussion of any topic with a tangible enthusiasm that I'm sure most of you already know. He's backed by a distinguished career that covers that covers many, many years, 20 of them at MIT. And from this perspective, Phil has a solid base on which to seek new insights and ways of describing things, which we'll be hearing more of, I'm sure. It's a compliment for me to say that I never quite know where his talks are going to lead, and the one this morning is no exception. Phil, what do the heavens declare?
Gordon, I'm sure many people know what the heavens declare. It's, of course, a literary allusion to one of the strongest parts of the framework of our speech, the famous translation of the Bible, which goes to the 17th century by that wonderful, probably the best of all committees, appointed by King James. And in Psalm 19 of David, recommended to the chief musician, as everyone knows, the text of the 17th century, translating the poetry, now 3,000 years old, tells us, the heavens declare the glory of God, and the firmament showeth his handiwork. Day unto day uttereth speech, and night unto night showeth knowledge. This, for me, is one of the most eloquent statements of what I think must be the chief source of the scientific temper in our species, which goes back far before even the poets of Jerusalem 3,000 years ago, deep, deep into the archaeological past, which we're only beginning now to grasp and understand. It seems quite plain, and this quotation has it almost explicit, that the order of the world, the sense that there is some kind of order pattern that we can perceive, has at least as one important source, of course, the motion of the game, the beat of the heart, all those things have their role. But the succession of day and night, the succession of the seasons, which we're all from the beginning so characterized and so marked, must have been one of the great stimuli to the look for order in other parts of the world, of our experience. And I think that's almost unquestionable. And that is the oldest. So in some sense, the astronomical rhythms, which are not, after all, evident, self-evident. Many jokes in all cultures explain how the sun is not so important as the moon because the sun is out by day when you don't really need it, whereas the moon. And this sense of causal relationship between day and night and the position of the heavenly luminaries, that's the sort of thing you don't teach in the schools. But there's no question, that's a fundamental kind of understanding of an abstraction, which everybody knows because that comes to the child in a curious way. And we have that idea. And so I think this is quite important. By the time you have gotten to richer body of scientific material, or proto-scientific material, say with the philosophers of Greece, who are so well documented, that's probably the only reason they stand out for us. They are well documented. We have their writings. And we know very well that they saw a commanding order in the heavens. And it was so grand for Aristotle that he and his followers divided the universe of our experience into two, dually, and said, here below, motion is haphazard and faltering and turbulent and chaotic. But above, it is circular, the most perfect of forms. Here below, matter is earthy and dull and multiple and impermanent. But there it is shining. And here below, things are born and die, things wear away and degrade and change and go. But up there is perpetuality. So they said the heavens are characterized by, they are circular, shining, and perpetual. And here on Earth, all our experience leads to the other sort of phenomena. And that is not a bad division of the world. It is the beginning of a theoretical understanding. I believe, and I will say that most of what we now know makes it deeply wrong, and we'll see how clearly that is. But it's wrong only in the sense that all initial approximations are wrong. It's transcended by a higher understanding. But right in its essence, yes, the heavens are different, but no, it is not that we are that different, because we too are in the heavens, circling around on a planet like the other planets, just as shining and circular, perpetual as they are. And it was the 17th century, the enormous rise of science in the 17th century, that gave the strongest enrichment of this idea, which was not the novel idea of the 17th century, but which blossomed then. On the one hand, the Earth was a planet and therefore shared these qualities. And on the other hand, the planets were not that distinct and different in another creation from the Earth, but no, part of the same. The moon was a place, said Galileo, and the crater he could see, he compared to a plain in Bohemia, flat and encircled by high mountains. And how could he say that? For the very best reason, he could lay eyes on it, and he carefully watched the sun rise on the mountain landscape of the moon in the winter between 1609 and 1610 from Florence and Padua. For the first time in the world, people could see enough detail to recognize that sunrise and sunset on the moon were parallels to sunrise and sunset in the mountains of Italy or Czechoslovakia. And of course, now the astronauts see the sunrise and sunset as they circle the world, but it's the same sunrise and sunset in a way which I think everyone clearly understands. It's not identically the same, but it has the same basis, the same origins, and the same geometrical and temporal description. He saw also that Venus was not the shining point that would have to be required if all planets were just like that. Venus showed phases like the moon to his telescope. And he knew the moon, of course, displayed phases, as the ancients had known, as we always have known. And so for Aristotle, the moon had to be a boundary place. It shared something of shining circularity and perpetuality, but not all. It shared something of the Earth. It was in between. Beyond the moon were the heavens. Below the moon was the Earth. The moon was on the frontier. And so, of course, we have made it in our time. The moon is still the only place reached by human beings beyond this Earth. The next unification was, of course, the remarkable, came very suddenly at the end of the same century, the remarkable rise under Newton, with a great deal of help from Hooke and Huygens and the others, who produced the idea of gravitation, universal force of attraction between all bodies of matter, not only Sun and Earth, not only Jupiter and his moons, but of course Earth and apple, as everyone knows from the old, perhaps true story of the fall of the apple. But I find it quite striking, as I'm interested always in this extension of these notions, I find it quite striking to recall that it took about a generation and a half, before the Royal Astronomer, Sir Neville Maskelyne, verified what Newton in his book, of course, had to recognize, what all the physicists then admitted and knew, that the bodies that draw each other here on Earth, like the book and not the Earth, but the book in my hand, have a tiny force between them, if Newton is to be right. Why is this force insensible? Why don't we notice it? Why is attraction restricted to the heavens or to the Earth, the great ball of the Earth, against everyday things? Only because of quantity, only because the force is so small. And it was Maskelyne who first had the brilliant idea, and carried it through, actually others had proposed, that if you made very careful surveys on either side of a mountain, he chose a mountain in the highlands of Scotland, and moved one side of the mountain to the other and used your telescope very carefully and your plumb bob very carefully, you could measure the fact that the plumb bob would incline ever so slightly towards the mountain. a mountain being about the smallest object that would give enough force to be detected by the instrumentation of that day. And it worked, and it worked, and he could measure the density of the mountain compared to the density of the Earth, and so on. And from then on, we have not gone without the direct knowledge. Now, an everyday experiment, not still an easy one, in the laboratory to show that lead balls do, in fact, attract something else in the laboratory. And of course, it doesn't have to be lead. But this sense of universal gravitation and the laws of motion that went with it unified the motion fully for hundreds of years of the development of the heart of mathematically aimed science, that's to say physics and the other natural sciences, from the time of Newton, from 1700, let me say, until approximately 1950 or 60. But without yet that final unification, which is to say, yes, we now recognize the Earth must be a planet. It must be shining, circular, and perpetual, so to speak. And the planets share the same earthiness that we have. We are all one. The universe is single. I'm very moved by the eloquent account that Galileo also made, though he was not the first. Da Vinci did the same, to describe the evidence for the shining quality of the Earth, not, of course, by going into orbit, as people now have seen it, but by looking for the reflection of the Earth light upon the moon. And his careful account of that, his analogies and comparisons and so on, innocent very much measurement, but using plenty of arguments derived from walking through the streets of Florence and watching the sun shine on different surfaces, he was able to show quite conclusively that the so-called old moon and the new moon's arm phenomenon is a phenomenon of earth shine from the clouds to the east of your observation point. And this is, of course, now nicely demonstrated, we have no doubt. And so when first a satellite went into orbit, a little cranky thing of 100 or 200 pounds with the errors, the designer, and the fingerprints of the machinist still on it, and then finally when human beings, men and women, also went into space, the final unity was established. It was not just mathematical, it was not just in the laboratory, but it was realized in everyday way, and that has had a great impact, I'm sure, upon the imagination of most people. See, what I'm talking about is not the specific things of astronomy, but the hold upon our own minds, the way we see the world, which all over the world has been dominated by these regularities and generalities that come from the pursuit of our place in the wider universe, that which we call astronomy in all its aspects. So I feel that the unity of motion and force was the sort of the second thing that we have, and its implications for everyday life, of course, are manifold, as an engineering institution bears witness. Newton's mechanics are taught just about in all departments. The next remark I want to make is the universality of matter, the unity of matter in the universe. Again, that was hard-won information, but signs were there. I just recently saw a beautiful analysis and photograph of a dagger owned by the Mughal Emperor Jahangir, about 1600, in which is folded in the middle of this wonderful dagger, beautifully inscribed, is folded a small piece of meteoric iron for a meteor that fell in the Punjab and was rushed to the emperor. They said it was something that came in a bolt of lightning, but it was obviously marvelous, and iron and stars have a name very much resembling each other in many languages, and probably the sign of this heavenly sent iron has had a big effect in the imagination of people. So there was some feeling that matter was not just here, and the mountains gave the form of the matter on the moon. When you see mountains, you know they're rock, though you don't really know that they're rock. They might be something that resembles rock, and indeed the scholastic critics of Galileo made much of this possibility and talked about glassy coverings and many other things I shan't bother, but the simplicity of the story really made its way known. And as I think all people who've studied some physics know, from these ideas of meteorites and pieces of iron, the spectroscope, which itself derived from the rainbow and from the color sense of human beings who can distinguish colors so well with the inborn gift of eye color, which most people have, not all, was demonstrable as a means of analyzing light itself without getting any sample. From light itself, you can penetrate the matter, which is the makeup, the composition of the source of the light. A truly remarkable effect, so that an exposure of a few photographs, or even looking with the eye in the spectroscope, is the same as getting a teaspoonful from a distant star and taking it to the chemist. In fact, on the whole, rather better. Probably takes much more than a teaspoonful. And we learned then that not only is it formed the same way, not only is matter earthy and so on everywhere, with of course, the exceptions, the sun is not. It's incandescent, and we understand that now. But matter, too, on Earth can become incandescent fleetingly. And so the sun is incandescent fleetingly. But fleetingly for the sun is a good matter of 10 billion years. So we have to understand these adjustments to the inborn human scale and human abilities. But it is the same stuff, the same chemical elements. And from the word you recognize, the word helium comes, of course, from the Greek helios, for the sun. And helium was an element discovered first by its spectrum in the sun and not known on Earth, but unmistakable even in the poor state of atomic knowledge of 1870 or 80 when it was discovered. The keen astronomers of those days said, yes, this is another atom. We don't have this on Earth. And it was found 25 or 30 years later in terrestrial samples. And of course now it's a commonplace of the stores and the birthday party, but it is really quite wonderful. It's lost to Earth mostly. We have it in very rare amounts because of its unique chemistry. It has no chemistry, and therefore the Earth lost it in early days. The sun is still 10%, 5 or 10% helium. The great planets are largely helium. Helium is a very common constituent of the universe, and we find, in fact, that the universe, nearly everything we see is hydrogen and helium. In fact, you say the universe that we can see in all bands, from the lowest frequency radio to the gamma rays, everything we can see is pretty much made and has the marks of hydrogen, technical grade hydrogen. Little helium, yes, and a certain amount of 2% impurity to allow for oxygen and iron and all the rest. Then you have a pretty good description of what the universe is made of. You could buy it, in some chemical warehouse, a technical grade hydrogen. They would sell you this mixture. And from that, all is made. All that we see. And of course, a wonderful sense of unity. And in addition, a sense of simplicity, of youth, of the pristine. Because if you ask what characterizes hydrogen and then what characterizes helium as a lesser secondary element, you find they are the simplest, the lightest, the least complex of all the stable atoms we know. And therefore, they suggest the processes are developing from simplicity to complexity, and this is a sign they have not yet gone very far. And it's a very important sign, and was a cornerstone of contemporary effort to understand the origins and fate of matter and of ourselves with matter, and is not, of course, without its criticism today. And I want to close with that, because, of course, we're looking forward always. We're not just looking backward. That is one of the great virtues of the scientific temperament, not always to its benefit, but it is a part of its temperament. We look forward. We look to the edge to see what more we find. And I simply wanted to close by saying there are two discoveries of the past 20 years, one perhaps the past 5 or 10 years, and one of 20 years ago, now quite elaborated so that they're almost, perhaps not entirely, almost beyond doubt. The first is that by looking at radiations, which we never expected to see, radiations in the microwave domain, the millimeter domain, very hard for us to measure, it became plain that the radiation that came from the dark parts of space between the stars and between the galaxies was much greater in amount, only hard for us to see, not made for our eyes, than all the radiation came from stars. When we examined this with detail, we found the remarkable, still unbelievable property to me, but unquestionable, its uniformity is beyond comparison. We know of no natural phenomenon in the celestial scale so uniform as the so-called thermal background radiation. It is accurately the same in all directions, day and night, summer and winter, north and south. You name any way you want to call direction. Comes from behind all the stars and galaxies, and it must go back to a time when the universe was still simple, when still uniform, when it had not made the complex, lumpy structures that we call galaxies, stars, planets, meteorites, people. And this sense, again, of turning from the simple to the complex is part of the story, which at least adds to the strength of the intuition we got from the pristine nature of hydrogen and helium. And then, as I indicated, not all is well, not all is so clearly understandable and a huge success. We are thrown into tremendous doubt and uncertainty by a wonderful discovery, which is now hard to doubt, hard to, on the superficial level, we may not understand it, but the fact seems to be true. All that visible matter that glows to us in all these wonderful spectral bands, some which can be seen from the Earth itself, some which have to go into space to see, all of those seem to bring us news. We now have gravitational evidence. The news that we get by electromagnetic radiation is news of only maybe 5 or 10% of all the mass that is out there, if we interpret the data in the most likely and simplest way. Most of the galaxies are mostly made of dark matter, so far invisible to all our instruments and detectable only by their now absolutely certain effect on the orbiting of the bright objects that we see orbiting around galaxies, which are little sample stars and nebulae that perform their orbits. And from those orbits, the physicists, the astronomers can make out what mass is causing them to gravitate, and that mass is simply too large to be accounted for by adding up all the stars and all the dust and all the gas and all that we see by a good factor, not just by a little bit, which we'd certainly expect, because there must be something we don't see. No matter how well you see, there's always a little more you can see if you had better light. So we expect a little bit, but the fact that it was not a little bit, but probably a factor of 10, is now the largest quandary, the largest challenge, I think, which is before us. We'll try very hard to find out what that stuff is. It's, of course, just possible there's something wrong with our explanations. Our law of gravity is wrong. Our laws of motion are wrong. That might be true. Many people work in that direction. I'm not excluding that possibility. But I think I am saying what most people believe, that there looks as though, for the first time, the wonderful guide that says, as it is here, so it is to some degree above, may be failing us. We may be entering into a domain where we see that what we see is only a decoration upon a vast, dark region of gravitating matter, probably left over from an early and much simpler condition, but a condition that whose simplicity we do not yet understand, because our laboratory techniques and our natural explorations have not yet given us a sample of the kind of matter we see there, or maybe they make hints of it in the highest energy laboratories. We don't know. That's the kind of problem which is fascinating to contemplate. That's the kind of problem whose solution many members, though perhaps not I, of this audience will see. And what an exciting time it will be. And this is the domain of astronomy to which the McNair building and the hard work of many engineering and scientific colleagues at MIT and around the world in the past decades have contributed, not anew, but as the last step, the latest, not the last, the latest step in that chain of human understanding and intuition, for which I think Psalm 19, a Psalm of David, is a very good introduction.
Thank you very, very much, Phil. We're not really in a situation to entertain questions this morning, so I won't encourage that. We're a little short on time. But if there were a really outstanding one, obviously, you're going to ask it anyway. Our next speaker is University Professor Charles Towns of the University of California at Berkeley, someone who is also very well known here, having served as MIT's provost from 1961 to 1966. Professor Towns is probably best known as the father of the laser, for which development he shared the Nobel Prize in 1964. His participation here today is highly appropriate, not only for his comments on astronomy and for man's role in space, but also as a representative of South Carolina, his home state, where Ron grew up. I note also that as MIT provost in 1963, Professor Towns played a very important role in arranging for and fostering the construction of the Space Center building that we are today dedicating to Ron's memory. Charlie, I think all of us are curious about your talk this morning. its title, Man and Creation, would seem to cover a lot of territory. So have at it.
Should I just use that? Or whichever. Well, thank you very much, Gordon. I am very pleased to be here, participate in this occasion, which is to honor Dr. Ronald McNair and dedicate the Ronald McNair building. I never had an opportunity to meet Ron McNair personally. Of course, I know his work in laser physics and his distinguished career as an astronaut, but there is also this other special reason I feel a very close affinity for McNair. He and I are natives of this relatively small state of South Carolina. So we both have the red clay and the sand of that state in our blood, and I share the communities and the atmosphere which nurtured him. Of course, being black, he had more external hurdles to overcome than I did, and I think we have to respect him all the more for his accomplishments. Ron McNair's life and the building which will be named for him have been dedicated to understanding the broader universe around us. That's an imposing assignment, but is nevertheless not completely out of touch with reality. To me, it's always been a profoundly challenging thought that we here, the recent creations of the universe, seem to be able to understand as much as we do about its workings and its history. We've discovered many, certainly not all of the processes which long ago brought about our own creation. It's particularly fantastic that we seem to have found this clear evidence, which Phil has mentioned, for the very origins of our universe, the Big Bang, going back in time some 10,000-fold beyond the origin of anything resembling ourselves. And that this creature's mind can begin to understand its own creation is quite startling. Logical or not, we even presume that man's mind has a chance of understanding itself. One hears increasing talk of the anthropic principle, that the laws of the universe had to be almost precisely as they are in order for anything like us to exist. Now, on the one hand, this can be taken just as a tautology. Since we exist in this universe, it must be of a style so that we can exist. It's obvious. On the other hand, the existence of man clearly required a particular arrangement of universal laws and constants, and even their fine-tuning. Another startling situation, startling to me, is that we now find ourselves increasingly co-creators in this universe. As Shakespeare's Hamlet exclaimed, "What a piece of work is man! How noble in reason! How infinite in faculty!" And I don't think he was just talking about the current number of professors. How infinite in faculty, in apprehension, how like a god. And yet, and he continued on, and yet to talk about some of his own personal uncertainties. So it's this infinite faculty on which I want to comment, but also the "and yet" part. Now, in some sense, all parts of our universe interact with each other, and in this interaction, each plays its role as a creator. This is evident all the way from the rather fuzzy principle of Mach, which says that the nature of space must be determined by what's in it, to the detailed and intricate role of each bit player in forming and modifying its own ecological surroundings and niche. Nevertheless, mankind shares an increasingly larger role as creator, affecting not only his own life and being, but having ever more responsibility for the nature of much of our planet. And we're about to launch into new responsibilities concerning both our own nature, through understanding of modern molecular biology and genetic engineering, and through space exploration, even the larger universe beyond our own planet. Now, this is an open universe, one for which the future is not innately determined. and one in which, through science and applied science, we are becoming more and more these co-determinants of that future. The uncertainty principle, which is relatively new, but has for some time, nevertheless, freed us of any idea of a complete determinism. We still fail to understand anything like free will, while nevertheless being instinctively convinced that somehow we possess it. In any case, there's no doubt that the effects of mankind's intellectual power and his actions are playing an increasingly powerful role in creating this world around us. And on the scale of planet's history, even on the scale of mankind's existence, this role is rather new and very rapidly accelerating. We need only be reminded that all of our written history is no longer than about 70 human lifetimes. And modern experimental science is perhaps no older than the length of, say, 5 human lifetimes. Much of the role of this unusual creature, man, comes through his understanding, his noble reason in Hamlet's terms. And yet, in spite of all our reason and science, our foresight as to what the future holds is in very important respects fuzzy, uncertain. This is partly the nature of creation. New ideas are indeed unforeseen. So we move headlong along, and usually with great anticipation, into a world we really don't yet know. The uncertainty and the struggle of creation is easily illustrated. Lord Rayleigh, the great English physicist who should have understood aerodynamics as well as anyone of his time, was quoted as saying, quote, "I have not the smallest molecule of faith in any kind of aerial navigation other than ballooning." And this was only 7 years before the Wright brothers took off from Kitty Hawk. Lord Rutherford, who was also perhaps the outstanding expert on the nucleus of his time, was able to say, quote, "Anyone who expects a source of power from the transformation of these atoms is talking moonshine." And this only 8 years before Fermi produced and his team produced the first sustained nuclear reaction. Well, whole committees of wise men have often been no less fallible. At the request of President Franklin Roosevelt, a commission, which can very reasonably be said to have represented a collection of the best minds and the senior statesmen in science and engineering of the time, tried to assess the future developments in science and technology which might affect American society and economy over the subsequent decades. Their report, issued in 1937, had some interesting things to say, but the most interesting is what the distinguished commission members missed. Because they missed antibiotics, which had already been discovered, but weren't appreciated. They missed nuclear energy, which came only 4 years later. They missed radar, jet aircraft, rockets, space exploration and our trips to the moon, computers, solid-state electronics and all its ramifications, lasers and quantum electronics, molecular biology, and of course modern genetic engineering. So we made a list of the most exciting technical developments of the following decades. That's what they missed. You know, creation necessarily pushes us into the unknown and often into controversy, frequently into danger. Ron McNair recognized and I think caught that very well in his phrase, hanging it over the edge. Because it is the edge of the unknown. Creativity also doesn't often come from this general wisdom of the time and committees, but rather requires individuals more than usually devoted to an idea and willing to accept uncertainties and risks. Creation often depends on individuals who are willing to take that extra effort, to be unusual, and to take these risks. Ron McNair was himself one of those who had the intellectual and the physical vigor and courage to go beyond the ordinary to the extraordinary. MIT has, of course, provided its share of creativity during the recent past, and we can look at those who associated with this building we talk about today, who've added to our understanding and the world's new technology. The people in that building will be creating new things which are different, but which nevertheless will parallel past discoveries here discovery by Bruno Rossi and his associates of X-ray sources outside our solar system, the distinguished work of George Clark in this area, discovery by Alan Barrett and his associates of the first molecule in space by radio techniques, Stark Draper's very striking development of inertial guidance, Herb Bridges' sounding of interplanetary plasmas, Gordon Pettingill's first exploration of the surface contours of Venus, or the exploration of human physiology in space of Larry Young and his associates. Now, new knowledge has two sides. One, the basic science side, is primarily cultural in nature. Discovery and understanding give us a breadth of view and inspiration, satisfaction of our innate wonder and intellectual drive, and a sense of creative achievement towards some of our most universal goals and ideas which are really our most lasting monuments. But there's also the application of knowledge, particularly scientific knowledge, to individual and social use, which is technology, engineering. These two sides are, certainly in modern times, closely knitted together, and perhaps they always were. They depend on each other in intimate and crucial ways. The importance of the cultural aspect is no less real because it's not so measurable and concrete. Nevertheless, it's clearly the technological aspect which most directly will be changing our lives. I was a graduate student when this Roosevelt Commission made its report. And recognizing all that's happened in the intervening 50 years, one can wonder what to expect 50 years from now, when I'm a little confused. Here we are. What can we expect 50 years from now when the students who are here at MIT today have an opportunity to look back over their careers and over their lifetime? What will be those discoveries of the future? Now, in my previous remarks, obviously I have to resist any vain attempt to make specific predictions. Nevertheless, there clearly are fields where exciting new discoveries are imminent. One, concerning the ultimate and microstructure of our universe associated with particle physics. Another, the rapidly developing understanding of biological systems in all their intricacy and beauty, including the ultimate challenge for the human mind to understand itself. Most pertinent to our dedication today is the exploration of the rest of the universe. That is, the universe which is outside our own planet, but at the same time so intimately tied with its creation and history. And how are these new discoveries to come about? And where, in fact, is man as a creator taking us? I think there are two extreme views towards this change and towards the future. One comes from fear and uncertainty, or at least reservation about the beneficence of any change in our society, change in the things around us. This was constantly manifest in the early days of exploration of our Earth, when new territories were looked on not only as barbarous and wild, but desolate and useless. Columbus, for example, was called in his time the Lord of the Mosquitoes. And it was really only about 100 years ago, Secretary Seward was pressing the United States to purchase Alaska and being joked about, and Alaska was called Seward's Icebox and Seward's Folly. I think this type of view might be cast in terms appropriate to today's dedication by a story of a little old lady who complained, why does everybody want to go off and explore space? Why can't they just sit home and watch TV like God intended? At the other end of the scale, yes, there are flights of fancy, for example, as illustrated by science fiction. It uses magical ways for everyday men and women to zip back and forth across our galaxy and visit multi-people planets. Magic because they defy basic scientific laws. Somewhere in between these, we'll see the future. Clearly, the creations of the future must obey the laws of the universe. But within these limits, the possibilities facing young people of today are really enormous, as developments of the last 50 years certainly illustrate. And I believe these possibilities are not going to be defined by our cold calculations of what we know how to do and can show is practical and comfortable at this point, but rather they will ultimately be determined probably by human aspirations as much as anything. It's partly for this reason that science fiction, which often reflects humanity's dreams, has elements of truth and prescience about the long-term future which are completely missed by many of the careful attempts to consider present practicalities. Our aspirations are critical for mankind's creations. And it's in this light that I expect the most recent report from the National Commission of Space is probably basically correct, that our species will be exploring space both to understand what is there, to make new living and working areas for humans. The Commission comments that the solar system is our extended home, proposes as basic parts of the space program that it should advance understanding of our planet, our solar system, and the universe, but also should explore, prospect, and settle the solar system. Now, is this latter practical? Perhaps not, certainly not immediately. But it is consonant with basic scientific laws and a prominent aspect of mankind's aspiration. And I believe such aspirations are fundamental to the nature of man and his role in this creation. They already say sending brave pioneers into space, and with time, advancing human knowledge and technology will make much of what is difficult quite practical. Of course, there'll be powerful changes back here on Earth, our home base, associated with advancing technology, probably many of them quite surprising. There'll be major steps in the conquest of pain, disease, hunger, provision of energy supplies and other facilities for increasing mankind's scope and activity. And how wonderfully each of us can think of this and envisage new creation, increase human capacities and progress. Mankind, how infinite in capacity, how infinite in faculty. And yet, there are also aspects of man's creations and aspirations which hang over us like a cloud. They raise critical questions about the value of our creations, even the viability of the species. Questions which might variously be called moral, ethical, religious, or perhaps philosophical. It is what we're really all about. What kind of responsibility have we as individuals or as a group towards this participation in creation? What kind of relations and what kind of organizations do we establish for this generation of humans? What kind of economics, politics, human freedom, or personal attitudes towards others? There is, of course, the question of war. But there is much more. There's this noble reason that man's understanding provides additional power over our environment and over our fellow creatures. What type of responsibility do we accept for them, or presently for the rest of the universe? As we understand and can increasingly modify biological systems, including the human species itself, how well prepared are we to have these new powers fit into some ultimate scheme of responsibility? Specifically, what striking new technological breakthroughs will occur is never clearly foreseeable, yet the general direction of science is quite clear. That is the direction of increasing power and hence increasing responsibility. And ever more urgency in these ultimate questions of who we think we are and what are our real aspirations and prospects as a species. These are really troubling and difficult questions. They are not new, but they become more poignant than ever. Creation has its real dangers. These questions are certainly not new to MIT, which has been notably involved in problems of society and the humane use of technology. MIT also provides an exceptional atmosphere for the interplay of ideas from different disciplines, and of the academic with the practical. So it's a good place for this laboratory and for the exploration of our universe and man's future. Because such questions and considerations were also clearly prominent in Ron McNair's thought and his own deep religious commitment. So as we rename this important laboratory to honor him, let's also honor his aspirations and the appeal which is expressed here, the booklet you have, his appeal, which in his words says, "Truly there is no more beautiful sight than to see the earth from space beyond. This planet is an exquisite oasis. Warmth emanates from the earth when you look at her from space. My wish is that we would allow this planet to be the beautiful oasis that she is and allow ourselves to live more in the peace that she generates." Thank you.
Our third speaker this morning is Dr. George Carruthers, Senior Astrophysicist at the Naval Research Laboratory in Washington, D.C. Following the receipt of his PhD from the University of Illinois in 1964, he joined the Naval Research Laboratory, where he remains today. I was interested to note that from his biography, like myself and others at MIT, he had training in nuclear physics at one time, which he has abandoned in favor of the wide horizons of astronomy. Dr. Carruthers is widely known and respected for his research in ultraviolet astronomy and received the Warner Prize for this work from the American Astronomical Society in 1973. Far ultraviolet astronomy requires an observing platform well above Earth's atmosphere, otherwise the rays are absorbed. And it was this requirement that made it natural for him to call on his training in astronautics, engineering, and place instruments in space using both suborbital rocket flights as well as Earth-orbiting spacecraft. Dr. Carruthers has been an active participant in the National Science Establishment, having served on various boards of the National Academy of Sciences and NASA, and he has been especially active in the affairs of the National Technical Association, a professional society for minority scientists and engineers, in which he also plays a very strong role currently as editor of the NTA Journal. This morning, he will describe the future of astronomy from space. Dr. Carruthers.
Good morning. I'm very thankful and honored to be here today and to participate in this dedication ceremony in honor of Dr. Ronald McNair. I regret that I never had the opportunity to meet Ron personally, although I had heard much about his remarkable accomplishments. And I'm thankful that I had the opportunity to meet some of his family and some of those who went to school with him when he was here at MIT. Today I'm going to be talking about the future of astronomy from space. I might mention that that was one of the major objectives of the shuttle mission in which he last flew, which had an objective to observe Comet Halley, which returns to the vicinity of the Earth every 76 years. Astronomy is the study of objects outside of the Earth, as Professor Morrison mentioned, such as the sun, planets, stars, and galaxies, and differs from other physical sciences in that its measurements are obtained mainly by remote sensing of electromagnetic radiation, which is emitted from or reflected from the object under study, rather than by direct experimentation or in situ measurements by sending a sample to the chemist. If I could have the first slide and the lights down. What we are showing here is the range of the electromagnetic spectrum. One normally observes visible light, which ranges from the red to the blue, but that's only a very small portion of the entire range of the electromagnetic spectrum, which ranges from extremely high energy X-rays and gamma rays through the ultraviolet, through the visible, and through the infrared, and down to the long wavelength radio radiation. Now, one of the problems is that classical astronomy has been limited to those wavelength ranges which penetrate the Earth's atmosphere. That's basically only the visual range and the radio range. Large portions of the infrared radiation and almost all of the ultraviolet, X-ray, and gamma ray radiation is totally blocked by the Earth's atmosphere and therefore is totally inaccessible to ground-based telescopes. Therefore, astronomy has been the science which has benefited perhaps most from space-based observations. Now, this next slide shows in more detail what I was mentioning previously, that the visible range and the radio range penetrate down to sea level, and therefore ground-based optical telescopes and radio telescopes are quite productive. But in order to observe in the ultraviolet and the X-ray ranges, one has to go to extremely high altitudes, above 100 miles altitude typically, in order to observe most of the radiation coming in from extraterrestrial objects. In the infrared, we're a little bit better off in that substantial improvements can be obtained by observing in aircraft and balloons at high altitudes above the lower atmosphere. But even in this case, we benefit greatly by going into orbit with our instrumentation. Now, there are a number of reasons why access to these new ranges of the spectrum are important. One of the basic reasons is that, as Professor Morrison mentioned, we can analyze the light coming from extraterrestrial objects to determine their composition. And many of the common materials, such as oxygen, hydrogen, and so forth, are totally transparent to visual light, and therefore you can't detect them by looking in visual wavelength ranges. By going into the ultraviolet and into the infrared, the spectral signatures of these common atoms and molecules can be more readily studied in extraterrestrial objects. A second very important reason is that the wavelength of radiation is related to temperature. As in the case of a simple black body radiator, which is not really a representative detail of what we would expect to see from stars and other planets, but gives a simple analogy. Ordinary visible light, which is here, corresponds to objects in temperature ranges between 3,000 degrees Kelvin and 10,000 degrees Kelvin, in which the radiator has its maximum efficiency. The total intensity of radiation increases very rapidly with temperature, but what is perhaps even more significant is that the peak, the maximum of the radiation, is temperature dependent. So for objects that are much cooler than the sun, for example, even a tungsten light bulb, which has temperature about 3,000 degrees Kelvin, is very inefficient at radiating visible light, and that's why we want to go to fluorescent lighting where possible, because it's more efficient. But objects even cooler than that emit primarily in the infrared, and that's why they don't emit visible light. Room temperature objects have their peak radiation at 10 microns in the infrared, and even cooler objects like 30 degrees Kelvin, which is the temperature that we see in some regions of dense interstellar gas and dust clouds, have their peak radiation at 100 microns in the infrared. Likewise, extremely hot objects, such as very hot stars and X-ray sources, emit most of their radiation at wavelengths well below the atmospheric cutoff at 3,000 angstroms. And therefore, it's very important to get instrumentation above the atmosphere in order to get more comprehensive observations of these objects. Now, what we have shown here is a series of planned space missions that NASA calls its Great Observatory Series. The Hubble Space Telescope, which I will mention a little bit more about a little later, operates in the visual range and also in the ultraviolet. The planned astronomical X-ray astrophysics facility makes observations in the X-ray range, which corresponds to very high temperature phenomena in the temperature ranges of millions of degrees. On the other hand, the Space Infrared Telescope facility will be operating in the infrared and will be making measurements of temperature regimes on the order of 100 degrees Kelvin, or much lower than room temperature, and will observe such things as interstellar gas and dust, which are totally invisible to ground-based telescopes operating in visible light. And at the extreme high energy range, the gamma ray observatory will observe even the very highest energy phenomena in the universe, such as nuclear reactions between protons and antiprotons, and things like that. So you see that in order to really get a complete study of phenomena in the universe, you have to operate over a wide wavelength range. Because if you only look in one wavelength range, such as the visual, you would only see a certain temperature range. If you only operated at very high energies, you'd see certain other types of phenomena. And same thing if you operate in the infrared, you see totally different phenomena there. So in order to get the entire picture, you really have to have instrumentation operating over a very wide range of the electromagnetic spectrum.
Third speaker this morning is Dr. George Carruthers, Senior Astrophysicist at the Naval Research Laboratory in Washington, D.C. Following the receipt of his PhD from the University of Illinois in 1964, he joined the Naval Research Laboratory, where he remains today. I was interested to note that from his biography, like myself and others at MIT, he had training in nuclear physics at one time, which he has abandoned in favor of the wide horizons of astronomy. Dr. Carruthers is widely known and respected for his research in ultraviolet astronomy and received the Warner Prize for this work from the American Astronomical Society in 1973. Far ultraviolet astronomy requires an observing platform well above Earth's atmosphere, otherwise the rays are absorbed. And it was this requirement that made it natural for him to call on his training in astronautics, engineering, and place instruments in space using both suborbital rocket flights as well as Earth-orbiting spacecraft. Dr. Carruthers has been an active participant in the National Science Establishment, having served on various boards of the National Academy of Sciences and NASA, and he has been especially active in the affairs of the National Technical Association, a professional society for minority scientists and engineers, in which he also plays a very strong role currently as editor of the NTA Journal. This morning, he will describe the future of astronomy from space. Dr. Carruthers.
Good morning. I'm very thankful and honored to be here today and to participate in this dedication ceremony in honor of Dr. Ronald McNair. I regret that I never had the opportunity to meet Ron personally, although I had heard much about his remarkable accomplishments. And I'm thankful that I had the opportunity to meet some of his family and some of those who went to school with him when he was here at MIT. Today I'm going to be talking about the future of astronomy from space. I might mention that that was one of the major objectives of the shuttle mission in which he last flew, which had an objective to observe Comet Halley, which returns to the vicinity of the Earth every 76 years. Astronomy is the study of objects outside of the Earth, as Professor Morrison mentioned, such as the sun, planets, stars, and galaxies, and differs from other physical sciences in that its measurements are obtained mainly by remote sensing of electromagnetic radiation, which is emitted from or reflected from the object under study, rather than by direct experimentation or in situ measurements by sending a sample to the chemist. If I could have the first slide and the lights down. What we are showing here is the range of the electromagnetic spectrum. One normally observes visible light, which ranges from the red to the blue, but that's only a very small portion of the entire range of the electromagnetic spectrum, which ranges from extremely high energy X-rays and gamma rays through the ultraviolet, through the visible, and through the infrared, and down to the long wavelength radio radiation. Now, one of the problems is that classical astronomy has been limited to those wavelength ranges which penetrate the Earth's atmosphere. That's basically only the visual range and the radio range. Large portions of the infrared radiation and almost all of the ultraviolet, X-ray, and gamma ray radiation is totally blocked by the Earth's atmosphere and therefore is totally inaccessible to ground-based telescopes. Therefore, astronomy has been the science which has benefited perhaps most from space-based observations. Now, this next slide shows in more detail what I was mentioning previously, that the visible range and the radio range penetrate down to sea level, and therefore ground-based optical telescopes and radio telescopes are quite productive. But in order to observe in the ultraviolet and the X-ray ranges, one has to go to extremely high altitudes, above 100 miles altitude typically, in order to observe most of the radiation coming in from extraterrestrial objects. In the infrared, we're a little bit better off in that substantial improvements can be obtained by observing in aircraft and balloons at high altitudes above the lower atmosphere. But even in this case, we benefit greatly by going into orbit with our instrumentation. Now, there are a number of reasons why access to these new ranges of the spectrum are important. One of the basic reasons is that, as Professor Morrison mentioned, we can analyze the light coming from extraterrestrial objects to determine their composition. And many of the common materials, such as oxygen, hydrogen, and so forth, are totally transparent to visual light, and therefore you can't detect them by looking in visual wavelength ranges. By going into the ultraviolet and into the infrared, the spectral signatures of these common atoms and molecules can be more readily studied in extraterrestrial objects. A second very important reason is that the wavelength of radiation is related to temperature. As in the case of a simple black body radiator, which is not really a representative detail of what we would expect to see from stars and other planets, but gives a simple analogy. Ordinary visible light, which is here, corresponds to objects in temperature ranges between 3,000 degrees Kelvin and 10,000 degrees Kelvin, in which the radiator has its maximum efficiency. The total intensity of radiation increases very rapidly with temperature, but what is perhaps even more significant is that the peak, the maximum of the radiation, is temperature dependent. So for objects that are much cooler than the sun, for example, even a tungsten light bulb, which has temperature about 3,000 degrees Kelvin, is very inefficient at radiating visible light, and that's why we want to go to fluorescent lighting where possible, because it's more efficient. But objects even cooler than that emit primarily in the infrared, and that's why they don't emit visible light. Room temperature objects have their peak radiation at 10 microns in the infrared, and even cooler objects like 30 degrees Kelvin, which is the temperature that we see in some regions of dense interstellar gas and dust clouds, have their peak radiation at 100 microns in the infrared. Likewise, extremely hot objects, such as very hot stars and X-ray sources, emit most of their radiation at wavelengths well below the atmospheric cutoff at 3,000 angstroms. And therefore, it's very important to get instrumentation above the atmosphere in order to get more comprehensive observations of these objects. Now, what we have shown here is a series of planned space missions that NASA calls its Great Observatory Series. The Hubble Space Telescope, which I will mention a little bit more about a little later, operates in the visual range and also in the ultraviolet. The planned Astronomical X-ray astrophysics facility makes observations in the X-ray range, which corresponds to very high temperature phenomena in the temperature ranges of millions of degrees. On the other hand, the Space Infrared Telescope facility will be operating in the infrared and will be making measurements of temperature regimes on the order of 100 degrees Kelvin, or much lower than room temperature, and will observe such things as interstellar gas and dust, which are totally invisible to ground-based telescopes operating in visible light. And at the extreme high energy range, the Gamma Ray Observatory will observe even the very highest energy phenomena in the universe. such as nuclear reactions between protons and antiprotons, and things like that. So you see that in order to really get a complete study of phenomena in the universe, you have to operate over a wide wavelength range. Because if you only look in one wavelength range, such as the visual, you would only see a certain temperature range. If you only operated at very high energies, you'd see certain other types of phenomena. And same thing if you operate in the infrared, you see totally different phenomena there. So in order to get the entire picture, you really have to have instrumentation operating over a very wide range of the electromagnetic spectrum. Now, what are the things that astronomers really want to find out? After all, when we go to Congress to justify new space missions, the first thing they say, well, you got these telescopes at Mount Palomar, you got the ground-based very large array telescope. Why do you need space telescope? Why do you need all of these other things? The problem is that there are still very important questions that are not yet answered about how the universe began, how galaxies formed, how stars and planets formed, and even the question of how life began. And as you can see, the modern field of astrophysics involves not just physics, but also chemistry and even biology. And these are all very fundamental questions of great importance to our whole society. Now, let me go on into a little bit more detail on some of these wavelength ranges. As Dr. Pettingill mentioned, my involvement has been in the ultraviolet astronomy area. And I'll just give a few examples of how that provides new information that we wouldn't have otherwise. On the right here is a ground-based visible light picture of the constellation of Orion, which is now prominent in the eastern sky right after sunset. And it's a prominent feature in the night sky because it contains a large number of very bright and luminous young stars. Many of these stars are much hotter than our sun, with temperatures of 30,000 degrees Kelvin or more, 5 times the temperature of our sun, which is 6,000 degrees Kelvin, and therefore most of their radiation is in the ultraviolet wavelength range. On the other hand, there are also many other cooler stars which are more like our sun, and perhaps most prominent to the visual, to the unaided eye, is the bright red giant star Betelgeuse, which is cooler than our sun, but very much larger and therefore more luminous. Now, on the left is a photograph obtained in far ultraviolet light with one of our instruments carried on a sounding rocket flight in 1975, which shows that the very hot stars are much more prominent in the ultraviolet than they are in the visible, whereas the cooler stars, for example, Betelgeuse, is totally absent in the ultraviolet picture. Now, what's perhaps even more significant than observations of nearby constellations such as this is when one goes to external galaxies. This is the nearest external galaxy, the Large Magellanic Cloud, which unfortunately is not visible from the northern hemisphere. But on the left this time is a ground-based visual light photograph, and on the right is an ultraviolet photograph which we obtained with an instrument on the Apollo 16 mission in 1972. And the ultraviolet imagery shows that the distribution of the very hot stars is quite different from the distribution of the cooler stars, which are prominent in the ground-based photograph. And since normally in external galaxies one cannot resolve individual stars, it's much more practical to have a survey such as this, which shows immediately where these stars are located, than trying to examine each and every image of a ground-based photograph to try to decide which ones are hot stars and which ones are cooler. Now, in order to study hot stars in more detail, NASA has launched a series of unmanned observatories beginning in 1968, the Orbiting Astronomical Observatory Series, OAOs 2 and 3, and also the International Ultraviolet Explorer satellite launched in 1978, which is still in operation, and which provides much more detailed spectroscopic information as opposed to the direct imagery that I showed in the first 2 slides. And they have made measurements of interstellar gas, hydrogen, oxygen, molecular hydrogen, carbon monoxide, things of this nature which are undetectable with ground-based telescopes. Going to higher energies into the X-ray range, this is a picture of a large area X-ray detector which the Naval Research Laboratory provided for the first high-energy astronomical observatory, which was launched in 1977, I believe. And what we see here is a quite different map of the sky in X-ray radiation from what we see in ordinary visible light. As I mentioned, the X-rays are emitted by extremely high energy and high temperature processes, and these correspond to such things as the active nuclei of galaxies, which are shown color-coded as yellow, supernova remnants, which are the remnants of exploding stars, such as the Crab Nebula, which I'll show you a picture of in a second, binary X-ray sources, which include extremely compact objects like neutron stars and black holes, which cause gas to be drawn into them, and when they collide and form an accretion disk, they produce temperatures in many millions of degrees, which are extremely powerful sources of X-rays. And there are several other types of sources which are shown here. Now, the second high-energy astronomical observatory, which is shown here, provide more detailed imagery of specific objects and also spectroscopy and X-ray radiation. And I believe people here at MIT had some involvement with this observatory. And it uses what is called a grazing instance telescope, which is quite different from the ordinary types of telescopes that one uses in visible and in the ultraviolet. And it had several types of detectors, an imaging proportional counter, and a crystal spectrometer, among other things, which were used to study the images of objects and also their spectral distribution in the X-ray region. The advanced X-ray astrophysics facility will be a larger version, but otherwise very similar to the HEO-2 spacecraft, which was called Einstein. The Crab Nebula is what we call a supernova remnant, the remains of a massive star which exploded in 1054 AD. At the time of the explosion, it was so bright that it could be seen to the naked eye in daytime. All that is left now is this expanding cloud of gas and a compact neutron star, which is the collapsed core of the star. Now, it took quite a few years before astronomers really understood what the neutron star was, and it turns out that it's quite visible in this picture. It's just that nobody recognized it until they found out that it was pulsating at 30 times per second. And it was quite accidental that they discovered that pulsation in visible light, although it had been known previously in the radio, and also occurs in the X-ray range. And the HEO-2 Einstein imaging proportional counter gave this image of the central region of the Crab Nebula, showing the neutron star remnant and this cloud of X-ray emitting gas, which is excited by high-energy electrons produced by the collapsing and rapidly rotating neutron star. So those are just some examples of the kinds of things that we have found out. Now, going to the other end of the spectrum, in 1983, NASA launched the Infrared Astronomical Satellite, which made the first measurements and the first sky survey in the infrared spectral region, which provides information about star formation and cold concentrations of gas and dust. I won't go through the details of how this is put together, but in order to explore very cold objects, you have to have a very cold telescope. This telescope is cooled to the temperature of liquid helium, which is about 4 degrees above zero, absolute. The reason, of course, is that it's analogous to trying to observe stars in visible light with a red-hot telescope. You have to have the telescope cooler than what you're looking at in order to make effective observations. This is the constellation of Orion again, just to orient you as to what it looks like in the visible. You'll notice that there is a somewhat deficiency of stars in this region here, which is due to a dense cloud of gas and dust. But when this is looked at with the IRAS satellite, we find that this dust is quite luminous in the infrared, even though it's very cold. The red color here indicates material at temperatures on the order of 30 degrees Kelvin, whereas the blue region up here corresponds to hotter dust which exists within our own solar system, the region of gas and dust in the solar system which is responsible for the so-called zodiacal light. But what we're really interested in here is that this interstellar material is quite prominent in the infrared, despite its extremely low temperature. And one of the most important objectives of the IRAS satellite was to observe regions in which new stars are forming, such as the region of the Orion Nebula, which is prominent in the visual also. But regions of star formation cannot be observed in the visual because not only the low temperature under which this process occurs, but also because it's hidden by the dense clouds of gas and dust, which are totally opaque in the visual, but which are transparent in the infrared. This is another example looking toward the center of our galaxy. The center of our galaxy is about 30,000 light years away, and it's totally hidden by dense clouds of intervening gas and dust, which the visual light cannot penetrate. We can only see that there is a denser region of stars in that general direction. But in the infrared, where we can see through that, we can see all the way through to the core of our galaxy, which is quite prominent in the infrared. And we can also see all of these regions of newly forming stars scattered along the plane of our galaxy. The advantages of space observations that I've mentioned up to this point have concentrated on the availability of a wider range of the electromagnetic spectrum. However, there is another very important advantage of going out into space, and that is that we are freed from the obscuring and distorting effects of the Earth's atmosphere on astronomical observations. Many amateur astronomers don't realize it, but the largest ground-based telescope, like the 5-meter or 200-inch telescope at Mount Palomar, does not provide any better resolution than a moderate-sized amateur telescope of 12 to 16 inches aperture. And the reason is that the distorting effects of the Earth's atmosphere blur the images to typical resolutions not better than 1 second of arc. 1 second of arc is about 1/1800th the size of the full moon in angular size and corresponds to the size of a dime seen at a distance of 2 miles. It sounds like good resolution, but it really isn't when you consider the capabilities of a large telescope from fundamental optical principles. By going out into space, we can greatly improve the resolution by freeing ourselves of these distorting effects of the Earth's atmosphere. The Hubble Space Telescope, which is shown in diagram here, is very similar to a typical ground-based telescope. And in fact, it's not really very large. It's only a little less than 3 meters in aperture, which is, it's 2.4 meters in aperture, which is almost exactly half the aperture, or 1/4 the collecting area of the Palomar telescope. However, because it's out in space and free of the distorting effects of the atmosphere, it will achieve an angular resolution of better than 0.1 arc seconds, 1/10 of an arc second, or 10 times better than the largest ground-based telescope. Also, because of this better image resolution, it will be much more sensitive to studies of astronomical sources, particularly faint point sources like stars. So we'll be able to observe a particular brightness of star to a 7 times greater distance than the largest ground-based telescope. The space telescope will be carried into orbit by the space shuttle and will be deployed, and as shown here, will operate unmanned for periods of up to 5 years before it's revisited by the shuttle to change out instrumentation. And during the time that it's free flying in orbit, it transmits its data to a tracking and data relay satellite, which then in turn transmits the data to ground-based ground stations. I mentioned that the resolution of the Space Telescope is 10 times better than typical ground-based, and this gives you an example of what this means. This is a picture of a nearby external galaxy taken with a large ground-based telescope, and the detail that we will be able to obtain in a nearby galaxy will be comparable to the detail provided by the ground-based telescope in our own galaxy. Factors of 10 are quite important in astronomy. This is the Andromeda Galaxy, which is the nearest large spiral galaxy, very similar to our own in size and shape. It's at a distance of about 2 million light years. And large ground-based telescopes can just barely resolve the individual stars in this galaxy. Actually, even a star as faint as our sun is invisible at the distance of the Andromeda Galaxy with present ground-based equipment. However, there are a number of types of stars which can be observed in nearby external galaxies, which astronomers have found form important distance indicators, the so-called Cepheid variable stars. The absolute brightnesses of these stars are known to a fair degree of accuracy from observations of them in our own galaxy. So by observing these stars in other galaxies, we can determine the distance since we know how bright they are. However, ground-based telescopes, even galaxies 10 times as far away as the Andromeda Galaxy, is getting close to the limit of what some of these distance indicators are useful for in terms of determining the distance of these galaxies. If we go by the shapes of galaxies and their types, we can get some idea of distances out to perhaps 100 million light years, or about 50 times as far away as the Andromeda Galaxy. So you can see there are various types of galaxies, such as spiral galaxies and elliptical galaxies and various types of galaxies. By knowing the statistics on their sizes and shapes, we can get some idea of how far away they are. But if we go even another factor of 10 in distance to about the ultimate limit of the ground-based telescopes, this is about a distance of 1 billion light years. Although you can see that these galaxies are not stars, they're just fuzzy blobs, and you really can't say much more than that. Now, why is this an important problem? If you recall that the speed of light is the limiting factor, a galaxy at a distance of 1 billion light years shows us what the universe was like 1 billion years ago, because that's when the light left there. However, astronomers estimate the age of the universe to be somewhere between 10 and 15 billion years. So what we really want to do is be able to observe objects at 10 or 15 billion light years distance, so that we can really understand how the universe evolved. And you can see we're a long way from that goal. The Hubble Space Telescope will help us quite a bit, because another factor of 10 will apply to all of the previous slides that I just showed you. We'll be able to detect objects such as this out to 10 billion light years instead of 1 billion. The previous slide, we'll be able to obtain detailed studies of galaxies out to 1 billion light years, and objects in which we can study individual stars to perhaps 10 million light years, 100 million light years rather. Okay, now let me go on to some of the other things that are proposed. The infrared astronomical satellite had a lifetime of only 9 months because of the fact that it had a limited supply of liquid helium. Also, there are a number of improvements that we can make for more detailed observations in the infrared. So one of the highest priority missions of NASA is the Space Infrared Telescope Facility, which is an expanded version of the IRAS, and also has the capability of being revisited by the shuttle so that the liquid helium coolant can be replenished. It will be able to observe much fainter objects than the IRAS satellite, and will be able to obtain much better imaging and spectral detail. I've already mentioned that other future observations include the Advanced X-ray Astrophysics Facility, which will provide similar increments in capability over the HEO2 Einstein Observatory. and the Gamma Ray Observatory, which will make the first high-energy, very high-energy observations over the whole sky, which will be launched hopefully in 1990. Now, in addition to these great observatories, the future of space astronomy will depend to a large degree on much smaller and much less expensive individual experiments carried on the space shuttle and perhaps installed on the space station. Individual small astronomical experiments can make particular contributions in areas in which the Space Telescope and other facilities which are general purpose are not optimized. For example, the Space Lab version of shuttle missions allows one to carry small telescopes such as this solar telescope that was on the Space Lab 2 mission for observations of the sun, stars, and other objects in particular wavelength ranges which are not addressed by the great observatories. And also the fact that we have manned involvement in the Space Lab mission makes them much more flexible and capable than an unmanned satellite for many purposes. Another type of small experiment is the so-called Spartan. This is the Spartan 1, which was carried by the shuttle into orbit in the spring of 1985. And this had an X-ray astronomy experiment on it. And there are several other Spartan satellites in the series of observations planned for the future. So with that, I would like to conclude by saying that those of us who are in the astronomical field are looking forward to the advances in our knowledge which will be provided by space-based observations over the coming decade. To a large extent, the space shuttle will be a primary tool for carrying these instruments into space and as a base of observations, maintenance, and retrieval. And I and most others in the astronomical field are very excited by these coming attractions. Thank you.
Thank you very much, Dr. Carruthers. I think you've made the case for the measurement of astronomy from space very strongly, but I'm probably biased. So, the final speaker this morning is Dr. Byron Lichtenberg, who is also an MIT product, having done both his undergraduate and graduate work here. He received a doctorate in biomedical engineering as a Hertz Fellow in 1979, and in the same year began his involvement with several vestibular experiments which were conceived and constructed by scientists and engineers in both the Manned Vehicle Laboratory and the MIT Center for Space Research. Dr. Lichtenberg executed these experiments aboard the Space Lab 1 mission as payload specialist in 1983. He has a background as a pilot in the Air Force, where he's been twice awarded the Distinguished Flying Cross, as well as many air medals. And he brings a different perspective to this morning's discussion. He's actually been out there in space, and he can describe that feeling firsthand. Please, Dr. Lichtenberg, tell us what it's like.
Thank you, Gordon, the McNair family. It's really an honor for me to be here and participate in these dedication ceremonies today. I would like to stress a little bit more people in space. Ron was out there. He knew what it was like. And what I'd like to try and do in some small measure today is give you a little bit of an idea about what it's like. Although Ron and I worked here at MIT and we were somewhat in close proximity, we never met here. We met after he was taken into the astronaut program as a mission specialist, and I've talked to him briefly several times, and when I did that, his enthusiasm for space, his love of exploration, and his love of education certainly came through. I've heard him give several speeches, including one to the Massachusetts legislature in which he pleaded for more support for education, and that also applies to higher education, such as places at MIT, and I certainly heartily concur with his feelings in those areas. What I'd like to do today is give you a little bit of my impressions of space flight and people up there, what they're doing, why we're going out there. I would like to try and put it in the context of the types of things that we can do in space. Then I'd like to give you a brief idea about where we are hopefully going in the future in terms of people in space, science in space, and a wide variety of humanity in space. Finally, closing with a few slides of the Earth from space and give you a few of my personal recollections and probably some of the things that will be similar to what you've heard Ron say in the past about the perceptual changes, the things that come over you once you've flown in space, because it certainly does make a difference. So what I'd like to do is start with several slides. I am picking up the slides of our particular flight of Space Lab 1 back in November and December of 1983. And I wanted to start out by giving you a feeling for what the Space Lab is. It is a pressurized module that sits in the back of the Space Shuttle orbiter, and it also encompasses pallets of science equipment, as Dr. Carruthers showed you a minute ago, like the Space Lab 2 experiments. Now, this particular piece of equipment was built by the European Space Agency. It was designed to be able to act like a laboratory in space so that people could go up there, work in a shirt-sleeve environment as you would work in the laboratories in the Ron McNair building, for example, to send active participating scientists up into space to do their particular experiments. Just to prove to you that we really did go up there, some people still think it's done in a movie set. This is the Space Lab on our flight in the back of the shuttle. You can see it fills the entire diameter of the cargo bay. It's attached to the mid-deck area of the orbiter with a tunnel so that we have free and easy access in a shirt-sleeve environment to go in there to do our particular science experiments. Now, on every flight, we have a wide variety of people. Our flight was certainly no exception. We had 2 pilots who actually fly the vehicle, 2 mission specialists. Ron McNair was a mission specialist, career NASA astronauts, people who are scientists and systems engineers to run the vehicle and to do the experiments and to carry out a wide variety of duties on board. We also had 2 of us payload specialists. I was extremely fortunate to be one of those payload specialists chosen by the science community. We also had a European on board, Dr. Ulf Merbold, who was a materials scientist from Germany and chosen by the European Space Agency and also by the scientists that had particular experiments on this flight. To give you an idea of what it looks like inside, it really is a true laboratory. We have a series of racks similar to the 19-inch racks that we have here in the laboratories at MIT. It's a very roomy, spacious place to work. It gives you a great feeling, and it's so great that you're actually floating in air here, as you can see. It's a tremendous experience to be up there and to be able to work in space. The only regret that I had was that we didn't have enough time to look outside and see the Earth, and I'll try and remedy that when I get to my Earth slides in a minute. There have been 4 Space Lab missions that have flown so far. We flew in 1983. We had Space Lab 3, which was designed solely to look at material sciences experiments, a few life sciences in 1985. Space Lab 2 also in the summer of 1985 to look at solar astronomy and physics, and the German Space Lab mission in November of 1985, again looking at material science, life sciences, and some navigation experiments. But for Space Lab 1, we were really a demonstration flight. Our goal was to prove the Space Lab system, and to do that, we conducted experiments in many different science disciplines. I'm going to stress some of the life sciences ones today because we're talking about humans in space. We're talking about having people up there. And as I look at the space program, and starting from a child reading the science fiction that Dr. Towns talked about earlier, at that time it was science fiction. People were not going into space. We didn't have people in orbit, and we didn't have satellites going to the planets. It was really science fiction. And we've been able to make that come a reality, and as you're well aware, it sometimes takes a lot of sacrifice for that to happen. In the Space Lab, we can do a variety of experiments. We were busy growing plants, miniature sunflower seeds, to look at how they react to the weightless environment of space. There are many things that need to be done in plant growth in the future. We need to understand the basic mechanisms, the way plants sense gravity. And this gives us a more basic understanding of the physiology in the plants. But even in a more practical sense, we need to understand how we can grow generations of plants in space without degradation, because surely someday, as you've heard and will continue to hear, Our vision is in the stars, our future is there, we're going there, and we need to take our grocery store with us. And to do that, we need to be able to grow plants in space, to give us food, to give us atmosphere revitalization, and to recycle water, as well as aesthetic, pleasing environment up there, which is important to all of us. In the, oops, lost my slides there. In the areas of human physiology, things that are of interest now, primarily in a science sense, are those areas of cardiovascular physiology, looking at the heart, the blood system, the musculoskeletal system. We did a variety of experiments looking at these changes. And just to kind of tantalize you a little bit, I'll tell you that although the changes are not really severe and they are reversible, strange things happen. For example, in space, you lose between 15 and 20% of your blood volume over 7 to 10 days in space. Now, that levels out, and it's not a problem for long-duration flight, but there are problems and things that happen with the musculoskeletal system. The muscles get weak and atrophy. Your bones start to demineralize. They start to decalcify. And in fact, we lose something like 1% of calcium a month as we stay in orbit. So we need to better understand these things if we're going to make these dreams a reality, and we need to start doing the research, as you can see now, and we've been doing it. We also are subjects as well as experiment operators, and as you can see here, we're doing some investigations into the blood system. I turned out to be not only a biomedical engineer and an Earth observer and an astronomer and a space plasma physicist, but also a blood donor and a lab technician, all those in space. So you can see that we really gave of ourselves to go up there and to be able to look into these particular areas of physiological interest. We also did some human perceptual experiments where we're looking at changes that occur in how you sense your limb position and limb motion. Can you do the same types of tasks? Do you have the same accuracies of pointing or of estimating weights or masses in space as we do here on the ground? So we did several of these experiments as well, shaking small gray balls of different masses to be able to detect how large a difference we could observe in space. In the field which is more my specialty, vestibular physiology, looking at the way the human reinterprets the sensory sensations in space, the sensory changes that occur. The MIT group, along with Canadians, had a series of experiments looking at space motion sickness. Again, it's not a long-term problem, but it affects close to 70% of the people that go into orbit for 3 to 4 days during each flight. And while it's not totally debilitating, it can slow you down, it can mar your performance somewhat, and it's something we need to understand more about. So we conducted a series of experiments, again, as operators and test subjects to look at the inner ear system, the organs of balance, and what happens to those when you, in fact, have a fall in space that we create artificially here. Or what happens when you move somebody in space. Another set of experiments designed to look at the sensitivities of the inner ear. And in fact, what happens over 5 to 10 days is that the brain changes. It's adaptable. It starts realizing that there is no longer gravity pulling you down. We can't use gravity up there as any orientation cue. The brain starts to rely more heavily on the eyes, on the visual system. So we wanted to see what it did with this motion sensing system. So we would provide motions. We also had helmets and visual displays to provide a wide variety of visual stimuli to look at, again, how the brain reorganizes and how it readapts to that brand new environment that we've never experienced before. Well, there are other areas also. We did a credible amount of experiments in material science, growing new types of crystals, new alloys, investigating the basic physical properties of what happens to fluids and solids in space and how you can possibly come up with new concoctions. We also used the Space Lab as a control system for many outside payloads. The telescopes you saw earlier in Dr. Carruthers' talk on Space Lab 2 were controlled from computers inside the Space Shuttle and inside the Space Lab system parts. We also use many control systems to look at a variety of areas. We had experiments, as I said before, in astronomy and solar physics and Earth observations and plasma physics. And I'd like to show you a slide of very interesting plasma physics demonstration. This is not blood plasma now, but this is space plasma. This is ionized gases and particles. This is a beautiful picture of an aurora taken from the Space Lab 3 mission over the South Pole, so we can't call it the Northern Lights. have to call it the, I guess, southern aurora borealis. But you can get an idea of the beauty, even at night, of a very large-scale aurora. This is stretching all the way across the horizon from the vantage point of the shuttle. You can see very many cloud features. The energy released in this is just phenomenal. I'd like to point out also how thin and fragile our atmosphere is. This little brown band, just that wide, is all of our atmosphere. It's very striking when you see that the first time from space, even with your naked eye, and you realize that being up only 125 to 130 miles, that you're above virtually all of it, and looking down and realize that that's what's taking care of our entire planet. Some stars that we've seen before, we see from another view, and we also see several stars through the horizon here. But the main thrust in the plasma physics areas is on the energetic interactions, what happens when these energetic streams of particles come into our atmosphere and create these beautiful sights, beautiful and very powerful sights. This also takes a lot of teamwork. It takes many people, not just the 7 or 8 people that are in orbit, but many people on the ground to put the vehicle together, to help make decisions, to watch over all the things that are happening. So we have a very large ground contingent of people. There's an incredible amount of teamwork that goes into one of these particular missions, and as we all know, you have to rely on an awful lot of people to help you. I'd like to change now a little bit from doing science experiments in space to looking ahead and looking at what some human capabilities in space are for several minutes. We've seen pictures of astronomy telescopes being deployed from satellites. This is the long duration exposure facility, which has been deployed from the shuttle. It is out there as a satellite now, looking at the long duration effects of space environment, cosmic rays, on a variety of materials. We've also come a long way from the Buck Rogers and the Flash Gordon that I knew in my books and comic books and TV movies. This was Buck Rogers. This was fantasy only 25 years ago. Now it's real. It's a reality. People go out there routinely and fly around as an individual satellite in their manned maneuvering unit, flying in space at 18,000 miles an hour, very accurately keeping time with the space shuttle. And we can now do a variety of things with these people out there in extravehicular activity. We've been able to bring in satellites into the orbiter and repair them, take them from being a derelict in space and rejuvenating them. This particular Solar Maximum satellite was fixed with the addition of a new power supply and new science experiments. One of our explorers is here in the middle, taking a quick trip down the payload bay with the manned maneuvering unit in the meantime. We've gotten into construction in space. Just a little over a year ago, about a year ago, some MIT experiments called the EASE experiments were put up on the orbiter in order to look at the ability of spacesuited astronauts to go out there and construct things in space, to actually build structures. The object here first was to verify that the training that was accomplished in underwater tanks, first done here at MIT and then at the Marshall Space Flight Center, were indeed accurate in predicting the amount of time and energy and workloads that are needed by people to do construction activities in space. NASA in its space station, which I'm going to turn to in a minute, is not sure yet how they're going to construct it. Will they send people out and build beams like this, or will they use automated boxes like this Access can to build the structures? And here you see Access putting out a reasonably large truss structure about 30 meters long, almost 100 feet out of the cargo bay of the orbiter, to take a look at very large structures, whether they can be done by humans or automated. The results, although not final, show that the humans did a very nice job, and also that the automated system could work quite properly. Well, why are we doing those things? Why are we going out there to build truss structures? Well, we're going out there so that we can create a permanent presence in space. This is President Reagan's buzzword that everybody uses. It's called a space station. To give you an idea of the scale, it's 500 feet approximately from tip to tip, from solar panel to solar panel, almost 400 feet high from bottom, if I can use that word, to the top. The orbiter is about 125 feet long. You can get an idea of the size of the scale of the activities going on, or that will be going on board the space station. And we need to have the data to understand how to put this up and how to use it. As I said a minute ago, the space station is going to bring an entirely new capability to the United States. We are, for the first time in a long time, going to be able to keep people up in space for long durations. We have to go back and take a look at the biomedical research that we've done in the past to make sure that we can keep people up there safely and happily. The current plan is to have people in orbit for about 3 months at a time. That's the duration of the experiments that we've had on Skylab back in the early 70s. Again, we found no irreversible changes. The Soviets, in contrast, have had people up for as long as 8 months. And although the data there is somewhat weak, they indicate that they have not seen any reversible or irreversible changes also. Although a lot of strange things happen. They find they have to bring their people back into a hospital for a month or a month and a half to recuperate. They have to bring them out of their vehicle horizontally on stretchers and very gradually expose them again to the full upright stance here on Earth. That may not be a problem coming back on a space shuttle from a space station, but if we follow the National Commission on Space and some of our earlier speakers and end up going to Mars or having permanent colonies in space, who's going to put that first hospital in Mars up? So we really need to understand what's going on, and these are some of the things that are happening. To give you an idea of the manned or the human presence in orbit, we'll have a series of beginning 4 modules. Each one of these 4 modules is about twice as big, twice as long as a Spacelab module. If you look closely, you can see the logo of the European Space Agency and also of the Rising Sun of Japan. It will be an international collaborative partnership effort with many different countries and people around the world. So we're learning to continue our collaboration and to work together, starting from the Spacelab series with the European Space Agency. We're going to have an entirely new group of people on board. We're going to need engineers, and we're going to need plant growth people and biochemists, and at some point we're going to need plumbers and electricians, and we're going to need gardeners, and we're going to need poets and artists, and every type of society that we have here on Earth will be into space eventually. And the space station is just one of our beginnings of it. Another idea or an artist's conception of what a laboratory might look like, to give you an idea of the scale of things and what's happening, we're going to be able to conduct long-term experiments in many areas of material sciences, of long-duration plant growth and human and animal physiology. I'd like to turn now to the last part of my talk, which is a little bit differently oriented. It's part of Earth observations. It's part of what people feel like when they go into space. And people tell you about the vibration on launch, or the initial sense of fullness of the head, or some of the physiological symptoms, or tell you in terms that I don't have the right words to put a mental image in your mind, but words of euphoria or floating, fantastic views, spectacular, the most amazing views out of sight. You can use all the superlatives you ever want, and I still don't feel that I can convey the beauty of the Earth from space. I think Ron has done it much better than I could, so I will leave it there. I have a series of space views that I'd like to show you. This is a lake in Canada called Manicouagan. It is very big. It was caused by a meteorite impact a long time ago, solid granite rock. The dimensions here are some 100 kilometers, 60 miles in diameter lake. So you imagine the amount of energy that was released when that meteorite collided with the Earth and formed that beautiful lake. Moving off to the east coast of Africa, if anybody is interested in meteorology or climatology or weather, you probably don't get turned on by clouds because you see them every evening on the television, as God had intended, I guess, sitting home watching TV. The one thing that you don't get from those satellite views of space and looking at the clouds and watching them bring rain or snow to your particular area, you don't see the three-dimensional aspects. You don't see the depth. And you won't see it on this slide either, but you'll have to trust me that it's there. As you look down from space, you can actually see the height of the clouds. You can see them attempt to billow up and touch the sky. Very beautiful, very striking, very large scale. Moving around now to the Mideast, we see very nicely nature and people living together. The bottom is the Red Sea going up through the Suez Canal to the Mediterranean Sea, the wonderfully fertile region of the Nile River Delta here. We see some very interesting round green dots, which turn out to be very large irrigation fields with the single-arm spray bars, where the Egyptians are reclaiming parts of the desert over there to make it habitable for people. Very large areas being reclaimed. Moving around to the Indian Ocean now, a very small, probably uninhabited island owned by France called Île Glorieuse. Very beautiful. The colors here don't do justice to what it's really like with your naked eye. The blues and the greens and the whites of the clouds and the yellows and the golds and the pinks and the purples of the deserts. It's just spectacular. It's just too beautiful to almost be able to describe. Some other very interesting geological features. This one in New Zealand, it's called Mount Egmont. It is a very lovely volcanic mountain with a snow cone on top. It was summer there. One of the things that we noticed very clearly is this big dark circle around there, and wondered what that was. And to give you an idea of how the New England people like their mountain also, they took a look at it and put a compass on the map, drew a circle around it, put a fence up, and called this all their national park land. So all the sheep grazers are out here on the outside, keeping the grass down. So you get a good idea of land use here just from the color change over in New Zealand. Moving on to Russia. Now, this is the Kamchatka Peninsula. It's a very active volcanic region. As you all are aware, when you circle the Earth at reasonably low altitudes, it takes about an hour and a half to go around. Well, that very nicely goes into 24 hours, so you get 16 orbits a day, and so every 24 hours you come over approximately the same spot on Earth. You move slightly, but not too much. And every day that we'd come over this peninsula, we would see another volcano that was active. There are more than a half a dozen volcanoes in here, active ones. You see one right here, and there are a bunch of them coming through. The splendor of the Earth is really tremendous. Remember, this is Russia. Notice that it's not in red. A lot of people still take a look at the maps and say, well, what do the borders look like? And the one thing you realize is that you don't see borders. The Earth is an extremely beautiful place. Sometimes you're lucky and you get to see Los Angeles. Here's one of those days when the clouds have been blown out to sea. You actually see the city of Los Angeles down here. Catalina Islands, we have San Diego to orient you. And I would like to point out some of the things that you do see. You can see runways, Los Angeles International Airport. You can see a general gray. You don't see individual buildings, but a general gray area. You can see some road structures, very nice grid structures up here and through parts of Los Angeles, so that you know that there are people down there, even from our vantage point in space. To sort of end the lecture and end on a note that I know or believe that, that Ron would agree with me on, and that is that the Earth from space is truly miraculous. As I said, you don't see the borders and the countries. You don't see the different cultures. You don't see all of our differences down here. What you do is you see one Earth. It takes an hour and a half to go around. It's very small in terms of time. And as you look up there and look down on it and be able to drink in the color of the Earth, you realize that we all share a responsibility to take care of it. So with that, I'd like to conclude, and thank you.
Thank you very much, Byron. I think it was a perfect counterpoint. I'd like to end the symposium here by thanking those speakers who contributed so much to the meeting today, as well as the other members of the planning committee that contributed to putting this symposium together.